Last week we tried to write the stiffness matrices separately for this example. Let me continue from here. For this example, when you have written the stiffness matrices separately, you can write, of course, but for our purpose, we need to create a superposition, or we will take all of these separate matrices and bring them together. Because of that, starting from different places, it is possible. Sometimes you can. It's not a rule starting from the first stiffness matrix, so you can create your own system from that perspective. Considering this, if we look at the definition of the problem, let me check here first. Yes, if you look at here, our first node is here, and we have got a second node here, and third node, fourth node, and the fifth node. If you are going to start with the first and second node, or you want to select between that one, it means you will start with the stiffness matrix 4, considering this. And starting with K4, you can continue with the connections. What are the connections? You have to look at the connections by node second here, and then you can go to from fourth one, you can go to for third one. So it means the order, if we select the K4 for the first element definition, you can continue, or initially you have to continue with the second node. After the second node, you have got a order, fourth or third. It's up to you. Considering this one, we have to create our superposition method and apply a global stiffness matrix, or combine from these ones and apply a global stiffness matrix. I don't want to spend much time. Because of that, I'm going to put the original solution document here. So you are going to start with K4. Let me mark all of the defining areas. K4, and you will continue with minus K4, and here should be plus K4. Because we have got 3 systems here, one of them is K1, which was started by K4, and then continue with K2. Because of the 3 stiffnesses here, first, second, and the third one, you need to collect them here, because all of them connected at that region. Which region? Node 2. So let me write the node 2 k1 plus k2 plus k4, and then I want to continue with, yeah, you can select it, it's not so important, but up to that one you have to change the order of the translations. Considering the U1, U2, U3, U4, U5, you have to keep that trajectory. Considering this one, I have finished the first and second node, and I have used the K4 matrix. Continuing from that to U3, you have to choose in order third node. It means you will use K2. So I'm going to continue with minus K2, and plus K2. After that, there is a connection between K2 and, look at here, K3. So I will take K3 then, plus K3, but look at here, the fourth node is here. So there is no connection with the third one and the fourth one. Because of that, you will make 0 here. There is no connection. What is the connection? Connection is going through fifth node. Because of that, you will make here 0 and then jump into fifth column. It means there is a connection between the third and fifth. So for that one also, you will apply the same thing, row and column also. So you will take the K3 minus K3, and then for the last one, fifth row, fifth column, it will be K3, but there are no connections also from here. If you look at the K1 here, K1 has got a connection with second one and the fourth one. So the connection will be for K1 is going to be here, the second, the fourth, minus K1, and the fourth row again, minus K1, and here. They are going to create different matrix systems. You have to consider all of these for the parallel and serial connections of a linear spring finite element. So this is the whole system definition for stiffness matrix, or let me say matrix of the stiffness after applying the superposition method. And you have already know that this matrix should be symmetric, which can be understood from here. If you draw line here like this. Yes, this one. You can see there is a symmetry. Look at here. Minus K4, minus K4, minus K2, minus K2, minus K1, minus K1, minus K3, and here minus K3. The others are all 0. It means it is banded, so we have got a stiffness value distribution at the orthogonal system of the matrix, which is named like banded matrix, and we have defined it before. Because of those definitions, we accept this one as a singular matrix also. So let me finalize this example, and I want to continue with a few more examples considering this direct stiffness method. Let me take this one from an example. I would like to give you a 2-element system, and this one, and we have got the stiffnesses. For the first element, 300 pounds per inch. For the second element, we have got 200 pounds per inch. I want you to create the, again, stiffness matrix systems, translations, and transformation or displacement vectors, force vector. If you want to write them separately, you can write them for the first element and the second element, and then you can bring them together or create a superposition. After that, what you want to do, you want to make the matrix simpler. Because of that, you will have to apply an elimination method to decrease the unknowns, and from that perspective you will make some of the unknowns 0. It is up to your knowledge, up to your knowledge of strength of material statics, and then you want to start with some of the elements that you are going to start with, especially the displacements first. After finding the displacements, you will take that values and apply to the loads vectors. So let me try to write the initial definition of the system. If I want to create an application, this one, for example, will be the first node. Here we have got second node, and we have got finally the third node. Yeah, you have got again one axis, which means you have got the x, and we will have got deformation or displacement systems. So I want to define the elements with the rectangular definition. This is the second element. And we know that K1, K2 are the stiffness matrices. And I want to give the displacements to the first element the direction is like that, which is D1, and for the second there is another external force, 30 pounds, was applied from the second node, but the definition for the displacement of the second stiffness, or the second element, let me say, it is D2. And again, we have got another definition at the end point. So it is D3 at here. But these ones should be after the creation of free body diagram. Let me correct it. Yes. And you will erase here like this. And again here. Yes. This is our problem's free body diagram. Now, starting with the separate definitions of the stiffness matrices, displacement, and force vectors. I'm going to start with the first element. Let me write here. For the first one, let's see, the value of it is 300 pounds per inch. So let me write 300. Or for the easy definition, I will make it out 1 minus 1 minus 1 1 for the 2 2 oops, sorry. Yes, and then I need to write the displacement vector d1, d2. I will make these equal to the force vector, which will be first element, first force, inlet, first element, second force, which is outlet. This is for the first element. For the second element, I'm going to write 200 again 1 minus 1 minus 1 1, and the displacement is this time d2 and d3. These are going to be equal to the force for the second element, inlet, second element, outlet. Yes. After this, I'm going to write the superpositioning. I will apply superposition method to the system and will create them. For example, for the element 1, we have made this one before. Like, let me show you. First element stiffness is applied to the system. There is a system combined with 3 nodes, but there is no definition for the second stiffness or first stiffness. Let me write for the first one, like we will have 300 minus 300. And before, I don't want to write the second stiffness. I'm just applying the first stiffness. So it will be 0 minus 300, 0, and these are all 0. I'm going to multiply it with the displacement vector d1, d2, and d3. Let me take these to appropriate position so we will have enough space maybe. Yeah. After that, I will make them equal to the force vector, which will be force first element, and because we have described just for the first stiffness, you won't write the third one, but you can write the displacement. If you make it for the second element also, first element will be 0, and here are, for example, 200 here, minus 200, minus 200, and 200, and for the force, the first element will be 0, something like that. I'm going to combine all of them together. So here we have 300 minus 300. This will be 0 because there is no connection. Again, this is minus 300. Here we will add 200 here because there is a connection. Where? At the second node. So this is the second column. Second column, second row. I will make here minus 200, 0, minus 200, and finally 300 for the third row, third column. And I will multiply it with the deformations d1, d2, d3. That will be equal to, for the first force inlet, for the first element outlet, and here we will add the second element inlet, and second element outlet. This is the general definition of the superposition two-element system. Finally, I would like to solve this equation. How? I know that d1 should be 0 because the system is mounted on the wall. Again, d3 will be 0. I have already know it. So initially, what was I doing? If you remember, we will make the elimination. So let me write it. Starting from here, for example, I will make here 1. Why? Because I don't want to look for d1. I'm going to erase here, erase here, erase here. But I want to approach to the unknown. Considering that equation, oh, yes, considering that equation, let me correct here, I have written wrong, that is 200. Yes, considering that one, I want to make the elimination, so here will be 0, final column will be 0, initially it will start with 0, this is the superposition of two stiffnesses, so it is 500, final column again 0, 0, 0 and 1. So I'm going to again apply this displacements D1, D2 and D3. It is going to be, because of here are 0, I will make the first force 0. And the final row is 0 again, so I will make here 0. The applied external force was 30 pounds, so I applied like this. When you solve this equation, you have got d1 equal to 0, d3 equal to 0 here, so d2 is equal to 30 over 500. So if I write the solution of the displacements, it will be d1, d2, d3, it is equal to 0.06 inches, and here again 0. So after finding these solutions for the displacements, I want to solve for forces, which means I can write the matrix system separately again. Let me write here. (300) minus 300 minus 300 we will apply displacements 0 and 0.06. This will going to give you, if you calculate it, 3 multiplied by 6, there is a 2 0 here, 2 after a 0 here, so it means 18. Because there is a balance, you will have, look at here, D1 is right hand side, but for the application of second nodal force, it is on the right hand side. Because of that, the true direction will be left hand side, which means minus 18. So here again positive 18, and these results are in terms of pounds. For the second element, 200 minus 200, continuing with the same manner, again the displacement vector. This time it's going to be start with 0.06 and 0. Let me correct these ones. This should be, I have written wrong initially. Here, sorry. First element, first force, and for this one again, I have written again wrong. Yeah, this one. Second element, second force, yes. After that, if you look at the total external load, it was 30 pounds. Initially, we have found for the first force, it is 18 pounds. It means that you have left 12 pounds, which you can also calculate from here. 2 multiplied by 6, it's going to give you 12. So let me write it here. You will have, but you have to consider the directions also. This one, because you are going to multiply it, you should multiply 18 with 12, which is going to give you 30 in total. And for the second row, because of the opposite directional system, it will be minus 12. Yes, we have solved the equations of finite element system. Let me write the separate definition of the elements. For the first element, you have got minus 18 pounds. And look at here, nodal system, spring element. Again, it continues 18. It is the first element. For the second element, again, the same direction. Look at here. It is 12. There is the second row, second node, and this is the second element, third node, and for the balance, 12, which is the second element. If you collect them together, I will give you for the total system minus 18 pounds, or left hand side. Our second node, we have, this is the reaction. These are right hand side, and this is just because of the free body diagram of the node 2. Because of that, you will write the directions of the forces opposite. It means this is also 12, and we have got in total right hand side 30 pounds. This is our final definition. So I have got another quick creation problem. Let me erase here, clear the screen first. Yeah, we have got a question. Let me draw it. initially there is a wall, and again we have connected our first node at the wall. This is the first element, which is connected to a plate here. There is another connection here, a parallel spring. Here is again wall. The same thing is also for here. There is another spring element. There is a connection to wall. And I am applying a force from here. Force P. And our direction is again at X. Let me detail the screen. And we have got slider here. Again a slider at bottom surface. When you apply the force P, the plate will be perpendicular to the top and bottom surfaces. It is going directly. It's not moving with angles. There is no rotation. There is only translation for this plate. So here, this is the first node. First stiffness value. These are the second connections, second stiffness, third node, and fourth node. Let me mark them. And this one also will be K3 for the third stiffness. Yeah, if you look at this definition, I want to give you not the solution, I want to give you a kind of definition. You can write also scalar numbers instead of letters. We have got a boundary condition like we already knew that u1 is equal to 0. There is no displacement here, connection to the wall. u3 and u4 also 0. If you look at the compatibility condition at node 2, you know, for the first spring element, second and third, they are all connected to a plate and holding them together. For the first element and part, for the second and third element, beginning of the springs. We can say that for the U2 first element, which is here, is equal to U2 second element is here, U2 third element is also here. Which we said that it is U2y because there is no rotation for this plate. There is only translation. Because of that, there is only one translation, only one displacement at that one. Let me write the nodal equilibrium conditions for the loads here. F1x, which means F first element, first, and the direction is x. I will make second row here a little bit empty. Let me continue with third one. F3x is equal to F, look at here, 3, it is start with second and fourth. So F3x, but starting point is 2. For the fourth node, F4x is equal to F, this time third, and there is going to be 4x. For the second one, we have got P force, so P is equal to all of the connections, first elements, first force, plus second elements, this time, second force, and third element, second force. So we can say that these conditions are here the sign convention for positive element of nodal forces. So when I try to draw the free body diagram of this one, let me draw here. For the first F1x, this is the node, and balancing first element, first force. This is for the node 1. For the element, I have start from here. I will now draw the first element. first element, first force, node 1, element 1, and here the second node, first element, second force. And maybe I will take these guys here to show you a little bit more. So this is the plate. We have got a force of balance here. Again, the same one. First element, second force at direction X. And these are the connections for node 2, all of them. So you can write 2, 2, and 2. There is a balancing force here. Second element, second force, and we have P here, P force, and here also third element, second force. Second means you are applying the second node. Because of that, I have written second next. You can change it. For the other free body, second element, the force is the same. I don't want to write it again. So maybe I should take here a little bit closer. Again, F2, 2x. This is the first element. This is the second element. And the outlet will be F2, second element, third force, 3x. Or you can write something like that, like in the example before. Second element, first force for this one. Second element, second force, yeah. Or second element inlet force, second element outlet force. If you don't want to write in this way, you can change it like in our initial descriptions. So here I don't want to write it again. Let me draw it. This time, third element, second force, third element, fourth force. Second and third. For the final free body diagrams, you have got again the same force here, and the right hand side is going to give us the response of the connection of the third node from the wall. 3x, and for this one, again the force is for the third element 4x, the same, node 4, this is the node 3, this is the node 4, and that is equal to, or going to balance it, f4x. When we use the local stiffness matrices, we can say that this is final definition for the direct stiffness method. Let me tell you. If you write it, let me write it here. F1x is equal to K1U1 minus K1U2. For the second, we have got P, and I have already written here. P is equal to minus K1U1 plus K1U2 plus K2U2 minus K2U3 plus K3U3 minus K3U4. This is for P load. For the third one, we have got F3x, which is going to be equal to minus K2U2 plus K2U3 F4x equals minus K3U2 plus K3U4. If I want to write these equations in terms of tensorial definition of finite elements, let me write the stiffness matrix superposition system here. K1 continues with minus K1, and if you look at the spring elements, we have got only connection with 1, 2, so it will continue. Third and the fourth elements will be 0 and 0. For the second row, you will start with the minus K1. Second row, second column, K1 plus K2 plus K3. And for the second nodal description, you have got a connection with K2, and you have got a connection with K3 in terms of U2 and U3. This time, the third row is going to start with 0, minus K2, K2, and finally 0. Now here again, start with 0, minus K3. This time, the center element will take 0, and finally, you got K3. Look at here, all of the descriptions. Let me show you. K1 description should create a rectangular system. For example, K2. This is the K2 definition. And for the K3, you will have here, 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 and here. You cannot write here. If you look at the systematic definition of the matrix system, those stiffness values will be in an order. So I will multiply this stiffness matrix with the translational vector with U1, U2, U3, and U4 will be equal to the force vector F1x, and for the second we have got external load P, and for the third row we are going to use F3x. Finally, we will have F4x. If you want to solve for U2, we have already defined many techniques and you can apply them, especially starting with elimination. You will make some of the displacements, and considering those ones, the forces will be 0 by applying it to the rows and columns. And don't forget to apply the orthogonal start, and the end ones will be 1. So you will find the displacements. After finding them, you can add it into the displacement vector and make it equal to the force vector. So you will finally get the load values. So I'm going to write here to maybe here definition of the deformation for node 2 will be equal to P over K1 plus K2 plus K3. So maybe I should take these guys here. Oh, sorry. I want to squeeze it or create an enough space for the final definitions. Yeah. Yeah, we have found the U2, and I want to add the forces. Look at here. We will have F1x is equal to K1 minus K1 multiplied by U2 for the F3x minus K2 U2 and 4x minus K3 U2. You can also write these guys together for creating the assembly, but we have already described the system. Look at here, let me mark it. This one is the global stiffness matrix of the system. So I'm going to define it like a capital letter of K. We have already talked about it. Yes, this one is the final example for our direct stiffness example. Let us come back and discuss about what we have done for the solution steps of the direct stiffness method. Let me clear here. Maybe you can study this example by changing the letters into the scalar values and try to find the real displacement and the forces of this system. So it will be a kind of study for you. If we look at the solution steps of these type of problems, we will have to choose a consistent problem units. So the units are very important, which means you can choose one of the SI units like meter, kilograms, or second, or centimeters, grams, second, something like that, or US definitions. It is up to you, but you cannot change it. For example, I want to calculate the stress values in terms of megapascals, which is going to be equal to Newton per millimeter square. So you have to use, for this type of application, millimeters per lengths and newtons per the loads. So if you have a kilonewton or something like that, you have to multiply it with 10 to the power 3 for converting the units to the newtons and megapascals, something like that. We have got a global coordinate system to define everything, and sometimes some subsystems you can add local coordinate systems additional. and label the nodes and elements to make the system simpler. And remember what we have done. We have given the number of the nodes, number of the elements, and identify the label and nodal unknowns. I know these things, I don't know these things, something like that. And identify the boundary conditions of the problem. What we have got, what we already knew, what we want to find first, what we want to find later, the connections to the walls, translations, which deformations will be zero, or roller connection, fixed connection, etc., etc. So maybe I should give a kind of algorithm to you for creating these solution steps of a coding. We have to write a loop through all elements, and this loop will be for the initial solution. Maybe you can increase the solution steps. It means that loop will be repeating again and again when you try to reach the exact solution or enough solution. And we have to form the element equations, create the equations, constitutive equations. And we will take those ones and assemble it into the whole system equations. Finalize the equations, or by applying the end of the loop, and after that you have to apply the essential boundary conditions, which we are going to learn in the future. We will solve these equations. We will obtain the secondary unknowns, which means, for example, in our problems, one of them is displacement and the other one is forces. After that, finally, we have to check the solutions if it's correct or not. And maybe I should add a little bit some about the theoretical notes. We have got an element stiffness matrix K. How is the K, if you remember? K is symmetric, but the rank of the matrix is deficient. That is important. Symmetric and rank is deficient. For the structural stiffness matrix of global K, I'm talking about global K, it is also symmetric. And the global stiffness matrix K is rank deficient before imposing the essential boundary conditions. And K is positive definite after imposing essential boundary conditions again. So, when we are started to describe 6 steps of the system, we have talked about maybe I should give again the descriptions to you so you can remember what we have talked before. We have got first discretization, which means creating the mentioned element equations, making them, taking them all of them together, create the assembly, imposing the boundary conditions, solution of the system equations, computation of secondary unknowns. We have already talk about these ones. Maybe to understand what is going on during your element descriptions or creating the tensorial system, maybe you have to draw a symbolic assembly. Maybe it's gonna help you to create the connections between the elements and nodes. Maybe let me show you something like that. For example, you have got a problem and you want to create the connections. You can use something like that. For the nodes here, first, second, third, and fourth, there is a connection at the node 5 with the elements 1, 2, 3, and 4. Something like that. And nodal unknowns. And if they are moving at just one axis, so it is going to be 1 degree of freedom per node. Yes, let's start to talk about the storage heaps. This is very important. Why? Storage schemes is going to give us details about how the computer will going to store the data into the memory by using the coding softwares like we offered you initially C++ for our applications, but you can use many other coding softwares, but C++ is the best one, I think, for applying the finite element method. Let me start with the definitions first. We have got a assembled global stiffness matrix, for example. So the shape of the matrix is, if the shape of it's something like that, we called these type of matrices upper triangular and banded matrix, which is let me show you. Upper triangle, you have got a triangle here, and banded means you have got bands here. Because of that, this is called upper triangular and banded matrix. Look at here, this one also tells us here is a symmetrical part of it exists and something like that. I have written here wrong. Let me change it to 4. If you write symmetry, it means on the 5th row K 5-1, K 5-2, K 5-3, K 5-4, and K 5-5. We have got an initial definition for these type of matrices. The initial definition called rectangular storage for this type of matrices. When you write this one, computer, if you choose a rectangular storage scheme, it is going to change your matrix into this. Let me draw it to you. Let me give it to you instead of writing. Yeah, the computer will change it into a scheme, something like that. Yes. This is called rectangular storage. How? This guy is going to take the orthogonal system into the column. Maybe I should show it to you something like that. You will rotate it and make it like this. So when you rotate that orthogonal system, this will be, again, if this is going to move 45 degrees in angle as a geometrical shape, and it will be here. So this one is should be 45 degree angle like this to move again right hand side, rotate in clockwise. So the initial matrix definition is changed and becomes something like that. So the important issue in the definition of the matrix, we are going to call it half bandwidth, which I will show it to you like half bandwidth of the matrix, stiffness matrix is 5. Half bandwidth, look at here, 1, 2, 3, 4, 5. But some of the schemes is changing it. So you have to look properly. So let me change this one. For example, I will give you an example, and I want you to create the rectangular storage scheme in terms of this way. So let me take these ones. Let me leave it to you as an example. So I'm going to change the matrix. Yes, if our matrix, upper triangular banded matrix, is something like that. Could you please convert the system up to the rectangular storage scheme? Try to write it. How you're gonna make it? You're gonna take the orthogonal system of the matrix and create a rotation about 45 degree, considering the clockwise rotation. So let me write how it's gonna be. We have got, maybe you can do something like that. Let's write like this. It is K11. So K22 will become second row, first column. K22. K33 again will come here. K33. K44. And finally K55. If I select here, if there is nothing written, it means they are all 0. Something like that. And if the matrix is symmetric, you will take these ones as a mirror application. So let me give this one. If all of these values become here, so I will take these guys perpendicular to the right hand side. So this one will be 0. For the third row, that is K13. For the second row, K22, K23, and for the third column, it is 0 again. K33, K34, and you will have finally for the third row K35. For here we have 0, again 0, 0, and 0. This is the definition in terms of rectangular storage scheme for a created or assembled global stiffness matrix. We have changed here, look at here. These values will be rotated around an axis, something like that here, about 45 degrees. But look at here. It is not. So it means that you are not changing everything. You are changing the orthogonal system, which means these will be because this is the basics and this is gonna be the half bandwidth of that matrix. This is defining the half bandwidth of the matrix. So this is a little bit different when you try to make it in the first one's definition, but you cannot see these guys. This is changing the columns, like here. It is changed like 3, 3, 2, 3, and 1, 3. The other guys will be on their initial position. You won't change the row location. You can change the we called column positions, but you won't change the row position like in here. And this is an example of creating half bandwidth with 3 and the definition is rectangular storage. So for this time I want to give you an example but I won't exactly solve it. I'm just going to give you to discuss about what is going on when we are creating the element descriptions, creating the stiffness matrices, etc. Let me give you an example. For example, we have a rod combining with two elements, and there are two loads applied again on the axis of the system separately. From the second node, we have given 10 kilonewtons at the x-axis, right hand side positive, and for the third node we have added 2 kilonewtons again. So let us talk a little bit. Initially we have to think about the matrix definition. So you have got K1, K2 here, right? If I am going to describe it with two elements, like one of it here and the other one, maybe I should draw here K1 and K2. If you try to create, how it's gonna be? What's the size of the global K matrix? Think about it. It is going to be 3 times 3, right? K1 minus K1. Is it something like that? Yes. Minus K1, K1 plus K2, 0, minus K2, and 0. 0, which means our matrix is 3 times 3. So how many 0 elements we will have? 1, 2, and 3. How many non-zero elements? For example, let me draw it. If I take this one and put it here, we will give displacement vector here, d1, d2, d3, and it's going to be equal to the force vector F1. If you write something like that, F11, F12 plus F21, right? F22, but don't forget, plus 10 kilonewtons plus 2 kilonewtons. So how many non-zero elements in F? You can think about it, etc., etc. You can draw the symbolic definition of the spring systems, etc. Finally, maybe I want to give you one more example for this one, for the assembly procedures. If we have a connection like this. We have got 4 nodes, 4 elements. So you can draw some type of tables to construct the global stiffness matrix in the superposition mode. So let me give you an example. For example, for the third element, I can say that third element, look at here. There is a connection with the node, the element 2 and the element 4. So you can write something like that, and when you are creating the assembly of stiffness matrix, you will maybe separate it, put some values between them, or you can keep something like that together. It is up to your construction, but in general it should be something like that. But for the third element, it's okay. If you remember, for our different constructed spring elements, you can face with different applications. Keep in mind. So let's talk finally a few more things and close this week's class. For example, assembling a symmetric, rank deficient K, which I can say yes. I want to create a symmetric and rank deficient little k matrix, which means k1 minus k1 minus k1 k1, a local, just one elemented k matrix. So if that one is symmetric and rank deficient, we already know that, and those matrices will come together and bring the global stiffness matrix into, again, symmetric and rank deficient. If the local stiffnesses are symmetric and rank deficient, the global matrix again will be symmetric and rank deficient. When applying the boundary conditions, I'm talking about the essential boundary conditions, it is needed to make the global stiffness matrix symmetric and non-singular. Don't forget it. When applying boundary conditions, essential boundary conditions, is needed to make K, global K matrix, symmetric and non-singular. And the location of the non-zero entries in global K matrix is a function of the node numbers, not element numbers. I'm telling it again. The location of the non-zero entries in the global K stiffness matrix is a function of the node numbers, not element numbers. Yeah, this is enough for this week. Let us continue for the next week, starting with solving linear algebraic equations. And until that time, don't forget to study hard. If you don't study, you will face with many problematic actions. Okay, the class is over. Have a good one.